Okay, let us wait for a few more minutes and then we can start. Hello, Vinay. Let us just wait for few 2 to 3 minutes, then we can start. Hello, 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 hello. Okay, so let's start. Welcome to week three's discussion session. I am Orko Chakraborty, a PhD scholar at IIT Kanpur. So, what we will be doing, we will be taking previous year's week three assignments, and I will be solving it for you so that you can get a guideline, or you can understand how to solve, how to tackle such kind of problems. Okay, so let us start. So the first problem statement is a true false. Here, let us look what has been asked. The first statement is, hope I'm audible, right? Can you kindly confirm? Okay, I think I'm audible. Okay, fine. So the first question is, the noise margin corresponding to higher voltage level is defined as noise margin high equal to V output high minus V input high. So let us look into it, and I'll be giving you kind of mnemonic to how to remember that, how to define the noise margin high and noise margin low. You can always recall it by the way I'll be describing it to you. Okay, so let us first look into the VTC of an inverter. Okay, so if you remember, if this was my V in and this was my V out, this would have been my VDD by 2, and the point where my gain was -1, let me call it point A, and this point as call that point B, this point as A. So this corresponding point is defined as V input low, and the corresponding output voltage of V input low is defined as V output high. Similarly, the voltage corresponding to this point A is defined as V input high, and the corresponding output voltage is defined as V output low. Okay, so basically this is my VDD, this is my ground, sorry, this is 0, and this is my VDDs, let's say. Okay, so what is V input low and what is V input high? Let us look into it. Okay, So basically V input low is the voltage, you can say it is the maximum voltage up to which we can consider the logic to be logic low at the input side. So any voltage between 0 to V input low can be considered as logic 0 at the input, and the voltage corresponding to what is V input high, and the voltage range, the minimum voltage range up to which I can consider the input logic to be high is called V input high or VIH. Okay, so this is the basically the definition of V input low and input high. Now, how to define the V output high and V output low, and why they are different from V input low and V input high. So basically what happens, uh, whenever we pass a signal, let me say I am passing a digital signal here, such kind of thing, through an digital circuit. Okay, so what will happen, I'll get some output. Now along with this output there will be some inherent noises in it. Okay, and I would try to ensure that the effect of noise, let me call it PB black box. So I will try that the noise present in the circuit doesn't affect my output voltage or doesn't change the output logic, because uh, if you see the circuits that we will be designing, one circuit, the output from one circuit will be fed to the input of next stage of such different circuit. Okay, and there will be multiple such circuits. So if some noise is present, here, this noise might change the logic, the intended logic of the operation, and what it will happen, it will lead to erroneous operation and lead to faulty results. To avoid it, we introduce the concept of noise margins. So what is basically noise margin? Let me draw it for you. First, I promise that I will be giving you a kind of mnemonic, so always remember this this diagram. See, the input will come in the middle, input high, input low, the output high, the output low, and this difference is called noise margin high, and this difference is called noise margin low. So the idea is that the output voltage levels should be, there should be some difference between the input voltage levels and output voltage levels, so that if there is some noise present here, still when it will be fed to the next stage, next circuit, it will still be recognized as a logic high or a logic low, depending upon the level I am working on. Okay, and if that noise exceeds this, then you can see that I'll be going to this region of operation, and my output will not be I'll not be sure what my output will be. That's why we ensure that there is a sufficient gap between the output voltage levels and the input voltage levels, and we define it by noise margin, how much noise the circuit can tolerate. Okay, so you can see from this diagram, and you might be familiar with this diagram also. Sorry, this diagram also. uh, Say it is my 0 volt, it is my VDD, it is my VDD by 2, then my initial okay, let's not jump into it, we'll come it next part, it will be useful for the next part. So from here we can say my noise margin high would be V output high, this V output high minus V input high. Okay, and noise margin low would be V input low minus V output low, this one. Okay, If you guys have any confusion, you can just stop me, and I will be more than happy to discuss it further. Okay. Okay. So the first statement was the noise margin. The noise margin corresponding to the higher voltage level is defined as V output high minus V input high. We can see it is defined as V output high minus V input high. So first statement is true. Second statement is the second statement is the noise margin corresponding to the noise margin corresponding to the higher voltage level is defined as V input high minus V output high. We have seen no, it is defined as V output high minus V input high. So the second statement is false. Okay. Similarly, the third statement is the noise margin corresponding to the lower voltage level is defined as noise margin low, V output low minus V input low. What we have seen, it is not V output low minus V input low, rather it is V input low minus V output low. So next one is also false, and remaining one, the final one, noise margin corresponding to the lower voltage level is defined as noise margin low equal to V input low minus V output low. We have seen, yes, it is V input low minus V output low. So the final one is true. So the result is true, false, false, true. So this one is the correct answer. True, false, false, true. Clear? Any confusion? I hope there is none. Okay. Okay, let me move to the second question. So again, a true false statement, some few statements are given, and we have been asked to identify whether they are true or false. Okay, the first statement is as the skew ratio gamma increases, noise margin low decreases and noise margin high increases. Okay, let us look into it. From previous day's discussion, you might remember that gamma was defined as beta p by beta n. And what is beta? Beta is mu p cox p w by L of the PMOS divided by mu n cox n by w by L of the NMOS. Okay. Okay. So let us look into the VTC of an inverter once again. See, this inverter is the basic building block. If you understand the inverter, you can design any combinational circuit, even sequential circuits. It is called the basic building, like the simplest circuit with which, if you know this one, you can build any circuit. Why I am saying so? Even when you work in device level physics, say you have come up with a new device. Say you are doing something with junctionless FETs, and you have proposed some new kind of device using some new interfacial layer or something new channel material or something. You have made the PMOS and NMOS. Now what you will be doing, you will be making an inverter with it, and you will be characterizing that inverter. The idea behind it is that if you know the characteristic of an inverter and the delay of an inverter, you can find the delay of any circuit that we can make using this particular device. And I hope you will be seeing that in the future classes, why it is so and why inverter is the building block. Even if you find the logical effort and all, you will be seeing that to normalize it, we always use an unit inverter. That is this inverter, the unit inverter. Okay, where it is 2 twice, it is 1. Okay, so it is called an unit inverter. We will always be using this circuit. So that's why the so much focus has been given here on the inverter and the VTC of the inverter. It is very important to understand how an inverter works, and you should know all the details of an inverter. Okay, how it is working, in which region of operation it is working. Then you can tackle any circuit that will come at your path. Okay, so if you remember the VTC that I draw in the last class. Okay. Okay, so let us call this as point B and this one as point A. Okay, Now if you remember, if we increase the strength of a PMOS, my inverter would move to the right hand side, right? I discussed that at great detail in the last class. Okay. Now see what happens. Why it happens? You are increasing the strength, means you are increasing the W of PMOS. So my beta P will increase. That is, if beta P is increased, implies my gamma has been increased, implies my PMOS will try to charge it much earlier, and that's why my VTC curve shifts in the right hand side. Okay, we have already seen that at great detail in the last class. Now let us look at what happens to the uh, noise margin due to this. Okay. Okay, so let me call the new point of transitions as B prime and A prime. Okay, this is B prime and this is A prime. Now let us look into this circuit. So see, basically this is my 0 volt, this is my VDD by 2, my initial trip point, and this was VDD. So my two swings, ground and VDD, and VDD by 2 was my trip point. So initially my noise margin was something like this. V input high, use a different color. This was V input high, this was V input low, and this was V output high, and this was my V output low. Okay, now what happens? So this was my noise margin, this was my initial noise margin high, and this was initial noise margin low. Okay, now when my VTC is shifted in the right hand side, you can see my trip point has increased from VDD to some higher value here. Okay, so my trip point, that is Vm, which was initially VDD by 2, has shifted now to a new value, say Vm dash. So accordingly my new V input high and V input low has also shifted, because it was defined with respect to trip point. Okay, that actually V input high and V input low, from where it is coming, from these points where my gain was -1. dV out by dV in was dV out by dV in was -1. So if my trip point is shifting, my VIH and VIL would also shift. I am calling them V input high bar, V input high dash, V input low dash. Okay, so now, but as you can see, V output high and V output low, they are not defined by my input signal, they are defined by my output swings and the noise margin. So my V output high and V output low has not shifted, and it has remained to its previous values. So you can see my new noise margin high has been reduced. New noise margin high has been reduced, whereas my new noise margin low has increased significantly. Okay, so like if you remember, I was talking in the previous class that we can use them to design sense amplifiers or something where we use shifted VTCs. So some of the problems that might arise while designing such circuits by shifting the VTCs is this noise margin, that the system becomes more prone to noise. The immunity towards noise reduces due to this shifting in the noise margin. Okay, so what is basically happening? So my noise margin, when gamma is increased, my noise margin high is reduced. So noise margin low would be and noise margin low is increased. Similarly, the opposite logic will occur when my skew factor, the skew ratio is reduced. My noise margin high would increase and noise margin low would reduce. Fine. Now let's look into the statements. The first statement was, as the skew ratio gamma increases, noise margin low decreases and noise margin high increases. We know it's false, it is the other way around, so it's false. Second one is, as the skew ratio gamma increases, noise margin low increases and noise margin high decreases. So we have seen it is correct, it is what happens, so it is true. Okay. uh, Third one is, as the skew ratio gamma decreases, gamma is decreasing, so this condition gamma is decreasing, my noise margin low decreases and noise margin high increases, so it is also correct, so it is also true. Finally, as the skew ratio gamma decreases, this condition again, noise margin low increases and noise margin high decreases, so it doesn't satisfy this condition, so it is false. So answer is false, true, true, false. False, true, true, false. Okay. Is there any confusion? I hope not. Okay. If you guys have any confusion, please stop me and ask me. I'll be more than happy to explain it to you again and again. Okay. Okay. Let's move to question number 3. Question number 3 is saying, again true false. It is saying, select true false for the following statements. V input high and V output low can be found by equating saturation current of PMOS device and linear current of NMOS device for an ideal inverter. Okay, let's look into it. If you remember in the previous class, I mentioned that in which region, in which part of VTC, in which region of operation my PMOS and NMOS were. So I will be looking once again into that. Okay, so basically circuit was something like this. It was VDD by 2. Say here it is VDD, it is V input, it is V output. Okay, it is VDD. So if you remember, I have divided that in few regions. Okay, so and say this. Okay, so first region was this region, say let me call it region A, and the conditions were, I have shown you in the previous class how they were coming, in which regions. If you have any confusion, you can just go back and look at that video. It will be clear to you. So my PMOS was in linear region and NMOS was in cutoff region, in this region A. In this region A. In this region B, my PMOS was still in linear region, whereas my NMOS was in saturation region. When it gets on, it enters the saturation region. And here where the trip point lies, let me call this region as C. This is where the trip point VM lies. Okay, here both PMOS and NMOS were in saturation region. Correct? And this region of operation D, my PMOS remains in saturation, whereas my NMOS shifts to linear region. Finally, in region of operation E, PMOS goes to cutoff region, while NMOS stays in linear region. So in the previous class you have seen the equation of trip point or this threshold point, voltage point of an inverter, and how we came into, how we derived it. And I also mentioned a line in the previous class. I also said a line in the previous class that my PMOS current and NMOS current is always equal. So what we did, we equated the, for finding the VM, as both were in saturation region, IDSN at saturation and IDSP at saturation, and by that we found the value of the expression of VM. Okay, so this is what we have did in the previous class. Now we are trying to find the V output high, V input high, V output low, and V input low. And where are these points? These points are here, at these points. So at this point, uh, so this is basically my V input low, this would be my V input high, this would be my V output high, and this would be my V output low. Okay, so you can see the region of operation is for V output high and V input low, V input low and V output high, the region of operation is PMOS is in linear region while NMOS is in saturation region. This one only. Okay, this region B, this region B. Similarly, for V input high and V output low, that is this region D, you can see my PMOS is in saturation region while my NMOS is in linear region. So what we will be doing, we will be just taking the current and we will be equating once again for this IDS of P in linear will be equating with IDS of N in saturation, and for this we will be equating IDS P in saturation will be equating with IDSN of linear, and we will be solving it. We will be easily getting the expression of VIL, VOH, VIH and VOL. This is basically nothing else. It's so simple. Okay, I prefer, more than learning the formulas and all, it is better to learn the ideas, how they are coming. Then you can derive them, or you can get the expression for any device, any novel device also, which has been just been fabricated or just been proposed. You can find it anywhere and you don't need to look into the formulas and all. So the idea how it is derived is much more important according to me. So you should understand how these are being derived and how we are getting these expressions. Okay, that's why I'm telling you in great detail how they are coming, how to obtain the expressions. So let us look into the statements. Statement number 1 is V input high and V output low can be found. V input high, this one, and V output low can be found by equating saturation current of PMOS, yes, and saturation current of PMOS device and linear current of NMOS device and linear current of NMOS device. So first one is true. Okay, second statement, V output high and V input low, this one, can be found by equating linear current of PMOS device, correct, and saturation current of NMOS device, this is also correct. So this is also true. And the remaining two statements are VOH and VIL, again this one can be found by equating saturation current of PMOS device, no, it's wrong, and linear current of NMOS device, it's also wrong, so it is false. Finally, the final one, that V input high and V output low, this condition can be found by equating linear current of PMOS device, no, it's saturation current of PMOS device actually, so it's wrong. And saturation current of NMOS, no, it's the linear current of NMOS device, so it is also false. So my answer is true, true, false, false. This one, true, true, false, false. Are you guys with me? Like, if you have any confusion, please feel free to ask. And I hope I am audible. If it happens that I am talking and no one is listening, I'll be very sad to know that. I hope I am audible, right? Okay, thank you. Okay. Let's go to the next question. Question number 4. Now question number 4 is little tricky. The calculation is really cumbersome, and like it, uh, I can still, while doing it, I can still do a mistake. So bear with me, and if I do any calculation mistake, just point that sir you are doing mistake in this step. Okay, and it will take a lot of space also. Okay, question number 4. So they have asked us to find VOH and VIL for an ideal transistor given the following matrices. Fine. Okay. They have asked us to find VOH and VIL. VOH and VIL. So it PMOS will be in linear and NMOS will be in saturation region. Fine. And this will be my let me draw the inverter here to help us to sort out the voltages and voltage levels that we'll be dealing with. This will be my V input, this will be my V output, and this will be VDD, this one will be ground, this one is source, this one is drain, this one is drain, this one is source. These are gates. Okay, now let's look into it. What we will be doing, we will be equating the currents. IDS of PMOS, which is in linear region, is equal to IDS of NMOS, which is in saturation region, right? So let us look into the expression. So we know in linear region the current is equals to beta P. It is VGS minus VT minus VDS by 2 whole VDS into VDS, and this would be equal to for saturation it would be beta n by 2, that is mu C of W by 2L into VGS minus VT whole square. VGS minus VT whole square. Now remember, this VGS and this VGS are not equal. It is for the PMOS case, it's for NMOS case, so we'll be getting different expression for them. So I think there are some conditions given that beta PMOS and beta NMOS are equal and VDD equal to 1 volt. Threshold voltage of PMOS is minus 0.3 volt and threshold voltage of NMOS is 0.3 volt. Okay, fine. So I can simply cancel them. So it will become 2 VGS. Now for the PMOS, my VGS is equals to V in minus V gate minus V source. Source is here VDD. And VT is minus 0.3 volts. Whereas my VDS would be V output minus VDD by 2 into VDS, which is again V output minus VDD, is equals to I have taken the 2 on this side, so it will be VGS. For NMOS, VGS is equals to V in minus ground minus 0 minus VT, which is VT of NMOS is equals to 0.3 volt. Correct? So let's try to solve it. Okay, so 2 V input minus VDD is 1 volt plus 0.3 volt minus V output by 2 minus minus plus VDD is 1 by 2 V output minus VDD is 1. Am I doing it correct? Yes, I think I am doing it correct. Is equals to V input is V input and minus 0.3 whole square. Okay. Okay, so now let me expand it and see what remains. 2 into V in, so it is 0.5, 0.5 plus 0.3 is 0.8, minus 1 is minus 0.2 minus V output by 2 to V output minus 1 is equals to V input minus 0.3. Now we will be trying to get the expression in terms of V out. We will be getting a quadratic equation and we will be solving it. Okay, so Okay, so v in into v out minus v in minus 0.2 into v out minus minus plus zero point 0.2. Okay, and then v out square by 2 minus minus plus v out by 2 is equals to v in minus 0.3 whole square, implies 2 v in v out minus 2 v in minus 0.4 v out plus 0.4 minus v out square, because 2 will cancel, this 2 and this 2 will cancel, plus v out equals to v in minus 0.3 whole square. Now let me take the v out square term, let me take everything in the right hand side and see what happens. It will become v out square, so let me cut them one by one, and let me take v out as common. It will become, let me take minus v out as common, so minus v out. So from this one I'll get 1, and this one I'll get 0.4, and from here I'll get minus 2v in plus v in minus 0.3 square and minus 0.4 plus 2v in. I hope all the terms have been taken care of. 1 2 3 4 5 6 7 terms. 1 2 3 4 5 6 7 terms. Okay, all the terms have been taken care of. Now, so if it is of the form of ax square plus bx plus c, where a is 1, b is minus, just give me a minute, v out 0.4, v out, okay, so to v in, I think I have done some mistake in terms of sign. If I've taken there v out, I've taken common, so it would be plus 0.4, it would be minus 1 and okay, sorry, v out so minus 1 plus 1 and plus, so it will be minus 0.4 plus 2v in, so it would be 2v in plus 0.6. Okay, so minus of 2v in plus 0.6, and c would be equals to 2v in, let me write it in this way, v in minus 0.3 whole square plus 2v in minus 0.4. okay, so we know that the answer is minus b plus x will be equals to minus b plus minus root under b square minus 4ac by 2a. okay, so here b, let me solve it for this term. Root under b square minus 4ac would be equals to root under, let me solve for this one, b square, so it will be equals to 2v in plus 0.6 whole square, minus square is plus, so minus 4 into a is 1, c is v in minus 0.3 whole square plus 2v in minus 0.4. okay, so let me solve it. 4v in square plus 0.36 plus 2ab, so 2 into 2 into 0.6, 4 into 0.6, 4v 2.4v in, so this term has been taken care of, minus 4 into V in square plus 0.09 minus 0.6 V in, this term has been taken care of, plus 2V in minus 0.4. So 4V in square plus 2.4V in plus 0.36 minus 4V in square minus 0.36 plus 2.4V in minus 8V in plus 1.6. So you can see this term will cancel, this term will cancel, and what is remaining is 4.8 V in. So it will be 4, this and this will be 4.8 minus 8 is 4.8 minus 8, which is equals to 3.2 minus 3.2 V in plus 1.6. So it is minus 3.2 V in plus 1.6. Okay, so therefore my x is V out, right? So V out would be minus B. What was B? Okay, so minus B will be 2V in plus 0.6 minus B plus minus root under B square minus 4AC, which is 1.6 minus 3.2 V in by 2 into A is 1. Okay. So now let me solve it. This is the expression of V out, and now we know at point where we get this noise margin, low noise margin, where we get VIH, VIL, VOH and VOL, the gain is -1. That is its fundamental definition, is equals to -1. So I will derivate this expression in terms of V in. It's very simple. So it will be 2 by 2, dV in by dV in is 1, 0.6 is constant, it will cancel out, so plus minus something x to the power half is half, x to the power minus half, so it will become half, and this 2 will also come, so again half, 1.6 minus 3.2 V in, from here it will come minus 3.2. okay, so it will be 1 plus minus 0.8 minus 1 implies minus 1 will be equals to 1 plus minus 0.8 divided by 1.6 minus 3.2 V in root under. So this sign will not matter, this sign will not matter because I'll be taking square anyhow. So minus 2 wholes, minus 2 by minus 0.8, sorry, let me write it another way. So 1.6 minus 3.2 V in whole square would be equals to minus 0.8 by minus 2 whole square, 0.4 whole square, which is equals to 0.16. 1.6 minus 3.2 V in is 0.16, implies V in would be equals to 1.6 minus 0.16 by 3.2, which is equals to how much? This is equals to 1.4454 by 3.2. Anyone has got calculator? Let me check. 1.44 divided by 3.2. It is coming as 0.45 volt. It is coming as 0.45 volt. This is my V input. So V input is coming as 0.45 volt. So this is my V input low. So this is the answer. And let us also check the V output. So V output we can find from this equation will be equals to, okay, so 2 into V input, 2 V input is 0.45, so 2 into 0.45 is 0.9 plus 0.6 uh, plus minus plus minus is root under 1.6 minus 3.2 into 0.45. So let me check how much it is. It will come 1.5 plus minus 1.6 minus 3.2 is 3. It is 1.44 divided by 2. So how much it is? It is 1.16. 1.5 plus minus 0.16 by 2. It will come at around 1.66 is 1.66. So sorry, 0.16 root under 0.16. So it's 1.5 plus minus 0.4 by 2. So minus it will not be, it will be 1.5 plus 0.4 by 2 is 1.9 by 2. It is 9.95 volt. Okay, so my V input low is 0.45 volt and my V output high is this is V output high is V output equals to 0.95 volt. So this is how we derive it. Okay, the calculation seems a little tricky, but if you follow all the steps, if you keep your mind calm, you will get the result. Even I was not getting this result. I was only getting V input and V output. I did not get in the previous attempts. But I knew that if I keep my mind calm and if I do it in front of you, if all the steps I do it correctly, the output will come, and the output came correctly. Okay. So while doing such calculations, just keep a calm mind and avoid silly mistakes. Otherwise, the whole calculation will be ruined off. If you do everything correctly, answer will automatically come. Okay. Okay, fine. Let's move to the next question. There is hardly any space. Let me try to move it. Question number 5. Okay, another calculation. Okay, let me shift this one. Cut the bottom. Okay, fine. Okay, so it is given that for a 65 nanometer technology node, the width is given as 1 micrometer, length is given as 50 nanometer, oxide thickness is given as 1.5 nanometer, epsilon ox, C load, VDD, thermal threshold voltage of PMOS, threshold voltage of NMOS, VDD expression, and its mobility is given. And it is said that the most important thing, it's a long channel model, and they have asked us to find the propagation delay for falling edge. Okay, so we know, I will simply, like, I can go and prove the TPDF expression, but it will unnecessarily, it will be of no use, because sir has already said in the lecture how to prove it, how to get the expression. I'll be simply using the expression that he already derived for us. So we know ln V out by VDT, that is VDD, VDD minus VT minus V out by 2 minus 0.693 is equals to beta n by C load TPDF minus TSAT V into VDT, that is VDD minus VT. Okay, fine. Now what, everything has been given, I just need to calculate this beta n and TSAT. I hope you have gone through the lectures, then it will be very easy for you to understand what I am saying. So let me calculate the beta n. Beta n is basically beta beta n is basically mu n Cox W by L of NMOS. So mu n mobility is given as 80 centimeter square per volt second. Cox is epsilon ox by Tox. Epsilon ox is given as 3.9 into 8.854 into 10 to the power minus 14 per centimeter, and Tox is 1.05 nanometer, 1.05 into 10 to the power minus 7 centimeter. I always say this, and I always give pressure to this thing, and I always mention this, is that always write the units when doing these calculations, because they ruin the answers during exams and all. I know, I have seen it, so it is always better to write the units so that you don't make any mistake and you get the correct result. And into W by L, so W is 1 micro, that is 10 to the power minus 6 meter, and length is 50 nano, that is 50 into 10 to the power minus 9 meter. I am writing it in meter because meter will cancel out simply, and here you can see this centimeter will cancel this centimeter square. So I will get 80 into 3.9 into 8.854 into 10 to the power minus 14 divided by 1.05 into 10 to the power minus 7 into 50 into 10 to the power minus 9, and here 10 to the power minus 6. So if anyone has calculated, do it. You will get the result as 5.26 into 10 to the power minus 3. This is your beta. Now let's find the T set. Now T set, this T set is equals to, I'll be again using the expression he has already derived for us, 2 into C load into Vt divided by beta n VDD minus Vt square. Okay, so C load is given as how much? Some femto, 20 femto, 10 to the power minus 15. Vt is 0.3. Beta n is coming as 5.26, 10 to the power minus 3, and VDD is 1, Vt is 0.3 whole square. Okay, so you solve it, you will get something as 4.65 picosecond. I have already solved it. You can go, you can check it. So I have got beta n, I have got T set. I will be using these two values. I'll be using this value and this value, and I'll be putting it in this equation. Okay. Therefore, ln V out is basically how much? Propagation delay is taken as 50% to 50%, right? So V out would be VDD by 2 divided by VDD minus VT is, say, let me write the expression first. V out is VDD by 2 whole by 2 minus 0.693 would be equals to beta n by C load to T propagation delay falling minus T set into VDD minus VT. Okay, let me write it. Log VDD is 1, 1 by 2 is 0.5, so 1 minus 0.3 minus VDD by 4, that is 1 by 4, it is 0.25 minus 0.693 equals to beta n was coming as 5.26, 10 to the power minus 3. C load was 20 femto, right, into TPDF minus, let me write it below, this one, let me write it here, it will be TPDF minus TSAT. TSAT was 4.65 picosecond, and VDD is 1, VT is 0.3. Solve it, you will get something like 0.588 20 10 to the power minus 15 by 5.261 10 to the power minus 3 into zero point 0.7. This zero point 0.7 will come here, and plus 4.65 picosecond equal to TPDF. Okay, so TPDF will come as 3.19 picosecond plus 4.65 picosecond, which will be equals to 7.84 picosecond. If you check 7.84, there is 7.72 picosecond. This one is the correct answer. This one is the correct answer, 7.72 picosecond. Okay, answer is 7.72 picosecond. We have taken some rough estimations. Some points I have avoided, so that's why I got 7.84 instead of 7.72 picosecond. Okay, but you will get the range, you will get the correct range of your output. Clear? Any confusion? Anyone? Okay. Let's move to question number 6 then. I hope the classes are not boring, right? I'm trying to explain it as much elaborately as possible, and if still you find it boring, or like you are not understanding anything, please stop me, please ask me. I'll be very happy to explain it to you in some other fun ways. Okay, just ask me if you find it difficult to understand. Okay, so next question is same. They've asked us to find this propagation delay, falling propagation delay, but now they've asked us to find it for a short channel model. Again, I will be using the formulas that sir has derived. They are doing nothing. How to get this expression of propagation delay? See, in any circuit, okay, before going it, let me talk about delay a little bit. Okay, for any circuit, okay, let me start by this. Say I'm having a MOSFET. Okay, channel length is L, say 50 nanometer for 65 nanometer technology that sir has been using, this one, and this is a velocity saturated device. So my Vset is given as how much? See, this one is my Vset. Vset is 10 to the power 7 centimeter per second. So if length is this much and Vset is 10 to the power 7 centimeter second, an electron is coming from Vd, one electron has entered from Vd. So how much time it will take to exit through source? Can anyone tell me? This is my length L and this is my Vset. So how much time the electron will take to complete this distance? It's a very important question and many students don't understand this concept. That's why I thought that I should bring it here. It is fundamental definition of delay that I'll be discussing right now. Okay, so anyone, please, anyone come and anyone say, if this is length and this is velocity, how much time would it take with this velocity for the electron to cover this distance? Class 7-8 maths. L by V. So L is 50 nanometer, V is 10 to the power 7 centimeter per second. So 50 into 10 to the power minus 7 by 10 to the power 10 to the power minus 7. Okay, so centimeter will cancel, second. Okay, so how much it is coming? 50 into 10 to the power minus 14 second, right? So minus, so it is 0.5 picosecond, right? So is it the delay? Anyone? Is it the delay that we are discussing about? Anyone? Bharat, Subrat or Vinay, anyone? Is it the delay that we are discussing about? The time taken by electron to cross this channel? Delay is time, right? So what is this delay? So yes, it is not that delay. Remember, here as we are saying that electron has entered from Vd and it is exiting through source. But remember, when this electron has entered this Vd, already one electron has left from this source. So we don't need to wait for this electron to travel and then the current will flow. No, it is kind of a, it is kind like electrons are most of the time what we say, it is a pipe. One water has entered, water has gone out. This is what flow of electrons are. But remember, it is like a full pipe. Already the water is there. When a small drop of water will enter, one drop will already go out. Similarly, when one electron will enter from this position, one electron has already gone out from this position. Okay, so this is not the delay that we are talking about. What we are talking about when we are discussing electronic circuit is capacitive delay. That is the time taken by the current to charge any capacitance. It might be load capacitance, it might be parasitic capacitances. So it is always charging or discharging delay. Okay, so that's why uh, even in diodes, this is this delay, that recombination time and everything we can describe in terms of capacitances. If you recall your first year basic electronics courses, BJT, same thing, we can describe the delay in terms of this. So my delay, if I write by delta t, is always some delta q by I, where delta q is change in charge and delta and I is the average current, or it might be average current or it might be instantaneous current. And if you use this definition, you can get the desired expression of delay to a good approximation. Say if the result is coming 0.8 second, you will not get 0.8, but you might get 0.4 second. If it is in 20 picosecond, you might get the result as 60 picosecond, but you will get the correct range, but just by simply using this expression. Now if you like even in CMOS, write the correct, what is Q? Q is C del V, and I is the MOSFET current, right? IDS. So if you break it and if you solve it, you will get the expression of the delay. How well you are defining the current and voltage and the capacitance, this will give you the accuracy. But this simply the del q by I, that is the time, the current required to, the current that is charging the capacitance, will give you the net delay, and not this one, not this one. This will not give, this one will give. Okay, so that is what I wanted to discuss. It's a very important concept, many people miss it, but you see, it is the basic fundamental in our field. This concept you have to understand it. Okay, okay, so how sir did it, how he has got this expression of TPDF and all? Nothing, he just considered I equal to CdV and V was the voltage, T was the time, and he knows the expression of I and values of C, and he has just substituted it, and he has got the expression of TPDF. That all this thing that he has solved by this, using this he has solved it. Okay, so the formula was for TPDF for a short channel device was nothing but VDD minus VT plus VC, VC is some constant, into C load into VDD by 2 divided by W into Cox, VDD minus VT square into Vset, where Vset is the saturation velocity of the carrier. Here as we are talking about NMOS, so saturation velocity of electrons. So TPDF would be, let me write it, 1 minus 0.3 plus VC is given as how much? VC is given as VC is given 1.04 into C load is given as I think 50, C load is given as 20 femto, 20 into 10 to the power minus 15, and VDD by 2 is 1 by 2.5. W is given as 50, sorry 1 micro, 10 to the power minus 6. Cox is epsilon ox by Tox, 3.9, 8.854, 10 to the power minus 14 plus centimeter, and Tox, let me write in the above part, Tox would be 1.05, 10 to the power minus 7 centimeter. Okay, and Vset is given as 10 to the power 7 centimeter per second. I hope everything is correct. Let me solve it. I'll be getting something as, getting the expression as how much? WC ox we said, and I'm missing this term, 1 minus VDD minus VT, 0.3 whole square. So if I solve it, I'll be getting 1.74, 0.5, 20 into 10 to the power minus 15, 1.05, 10 to the power minus 7, 10 to the power minus 4, 3.9 into 8.854, 10 to the power minus 14, 0.7 square, 10 to the power 7. Solve it, you will be getting something around 1.054, 10 to the power minus 11 second. That is 10.54 picosecond. So anything close to it, 10.54, 10.54 is 10.79 picosecond. This is the answer. Got it? Everything clear? Okay, fine. Now question number 7. Question number 7. Okay, so what has been asked here? It has been said that for k equals to 4, the switching resistance and the diffusion capacitance are, R is switching resistance of unit NMOS, C is the diffusion capacitance of unit NMOS. Okay, now what is K? K is the scaling factor, you can say. Okay, so if K equals to 2, that means I am using a W of 2. Initially W was 1 unit, now W is 2 unit. If K equals to 2, K equals to 4, W is 4 unit, and so on. K is 10, W is 10 units. Okay, so this is question number 7. Okay, so we know ID is equals to mu Cox W by L, VGS minus VT minus VDS into VDS by 2 into VDS. Okay, in linear region. Now we know this is the VDS versus IDS curve. This is the saturation region, this is the linear region or triode region. Now why this is called linear region? Because VDS and IDS are showing a linear behavior here. That is, my device is acting as a resistor here. Okay, it is called triode because here it is under control of three terminal, drain, gate and source on, and here only 2 terminals, gate and source, drain has no control, and it is called triode because drain, gate, source, all the 3 terminals have control over it. Okay, so now what is the resistance? Resistance, we know what is R. R is simply V by I. Here it is VDS by IDS. So VDS by IDS would be equals to 1 by mu Cox W by L, VGS minus VT minus VDS by 2. Okay, so you can see R is inversely proportional to W. Therefore, if my W increases, my R would decrease. Okay, and this can be also think like what is how W is affecting. If I see my MOSFET structure, this is my L and this is my W width. This is my width W. So what is area? Area is basically, if this is the thickness t, this much is thickness t, so area is basically w into t. So if you increase your w, your area would increase, and if area is increasing, my resistance, which is equals to rho l by a, as area is increasing, my resistance would decrease. Similarly, I know capacitance equals to a epsilon by d. So if w increases, my area would also increase, and hence my capacitance would also increase. Now therefore, when we increase the w, my resistance keeps dropping by the same amount, while my capacitance keeps increasing by that same factor k. Now this expression that I have written, how capacitance is increasing, it is true, as you know how many factors are there in a MOSFET that generally we talk about. There are mainly 5 kinds of capacitances: 3 oxide related and 3 body related. These are, if it is gate, drain and source, so these are CGD, CGS, this is body, CDB, CSB, and CGB and CBG is same, so another, it is called CGB. So there are 5 kind of capacitances, and all these 5 kind of capacitances is varies directly with W, but the reason is not same. Here we can see, as area is increasing, my C is increasing. This is true for some of this term of the 5 capacitances. For other terms, the variation with W, which is still as directly proportional, but the reason is little different. And you can look into the device physics of it. It will take some time, so I will not be discussing in detail why it is such, but you can keep in mind that resistance always reduces with W linearly, and capacitance always increases with W linearly. Okay. So, and there are, like, it is not of use, there are other capacitances also in a MOSFET called fringing capacitances. Okay, many capacitances come, depletion capacitances, fringing capacitances and all, but that's more device level thing, so we'll be looking here. Okay, so it has been told that, it has been asked that if k is 4, what will happen to my C? First of all, if W of NMOS is kept as W of PMOS, the ID of NMOS will be twice of ID of PMOS, right? Because mu n is twice of mu p. So that's why generally what we do, we take use WP as twice of Wn. Generally this is what we do, but here it is not mentioned, so we'll be taking Wn as WP to be equal. So my NMOS resistance would be half than PMOS resistance. Okay, so if unit NMOS resistance is R, my unit PMOS resistance would be 2R. Okay, so if I scale by 4, my NMOS will be reduced by 4 due to the reason that I have already explained here. So R NMOS would become Rn initial by 4, whereas my PMOS would become Rp initial by 4, and which was twice of Rn by 4. So let me call R by 4, so it would become R by 2. Okay, mu n, un is 2.5 up. Like mobility we're talking about. See, actually depends. Generally we take mu mobility of NMOS to be twice of mobility of PMOS. Okay, for simplicity of calculation, and even if you see when we'll be designing it, we'll be taking it, but actual mobility values will depend on the substrate that you are using, the doping that you are using, and it is in the vicinity of 2, little bit high or little bit lower than 2. And even in, like previously also I mentioned this, even in highly scaled devices like 6 nanometer, 5 nanometer, 3 nanometer, or even 12 nanometer, what happens, both mobility mu n and mu p are generally equal due to stress effects and all, but we can take the mobilities of NMOS with twice of mobility of PMOS. for circuit designing, it's a good enough approximation. Okay, it generally depends how much accuracy you want. If you want much more accuracy, like when you'll be designing the circuits, in the PDK all these values are already mentioned. So when it does calculation in the spice, it takes the values, it doesn't take simpler W, it takes the values and does all the calculations and give you the net delay and capacitance and energy and power and all. But the basic idea while doing the circuit design and all, we take the mu1 to be uh, twice of mu p, so WP is taken as twice of W1. Okay, one more thing, like in the rise time definition, sir has told that it is 20% to 80% is of the 0 to VDD swing. This is the definition of rise time. But in some cases, we take 10% to 90% instead of 20 to 80%. Why? Because on that time we require more accuracy. Some applications require more accuracy than the other. So we can change this. These are not nothing as hard and fast rules. We can change it depending upon our need and the accuracy that is needed. Okay, so these things, the exact value will be coming from the PDK, from the foundry, and just saying that it will be 2.5 times or 2 times, it's vague. It depends on the technology that you are using, and it varies from foundry to foundry because they change dopings and all. They use different substrates. Like global foundries will be using one thing, TSMC, Taiwan Semiconductor Manufacturing Company, will be using other, SCL will be using something else, and say IMAC will be using something totally different. Okay, so it is better, it is a good enough approximation to consider the mu1 to be twice of mu p. I hope it's clear, Vinay. Okay, okay, so my rnmos is r by 4 and rpmos becomes r by 2. Okay, and what happens to, so this is correct, this is correct, and as I said, both C, for NMOS and PMOS, it varies directly with W. So my C would become, C NMOS would become 4 of C, CPMOS would become 4, 4 of C. So this one is the correct result. R by 2, 4C, 4C. Okay, I hope it's clear. Okay, fine. Question number 8. For switching resistance of 2 kilo ohm, capacitance 20 femtofarad, what is the RC approximation delay? It's easy. Okay. Question number 8. Given RS 2 kilo ohm, F and capacitance is 20 femtofarad. Fine. Like in the first class, I proved how this expression of delay is coming, but let me do it once again. What I am doing once again, because I want to prove a point to you. That's why I'll be doing it again for you. Okay, so if you remember from the first class, we have taken a step function and we have called it the Vs. We have called it Vs. This is R, this is capacitance C. I'll be quickly going through it. This is, let me call it Vc, and let me call this as Vr. Let me call this current as I. So it's clear that Vs would be equals to Vr plus Vc. Vr is I into R plus Vc. I is equal to C dVc dt into R plus Vc. Why? Because C equals to, here for capacitance, I equals to C dV dt, right? So Vs equals to this. I will be taking it, I will be rearranging it. I will be getting something as dVc by Vs minus Vc equals to dt by Rc. Integrate it 0 to t and 0 to some voltage Vc. We'll be getting the expression minus ln Vs minus Vc 0 to Vc will be equals to t by Rc 0 to t. Fine. I have done it in the first class also. That's why I'm just spacing it out. So it would become minus ln vs minus vc minus minus plus ln vs equals to t minus 0 by rc, that is t by rc. So if I take minus common and take it to the other side, it will become ln vs minus vc minus ln vs, so it will become ln vs minus vc by vs equals to minus t by rc. So 1 minus vc by vs, 1 minus vc by vs will become exponential of minus t by rc. So from here we get the expression that vc equals to vs 1 minus e to the power minus t by rc. Okay, so now what we will do, we want what is the RC approximation delay. So RC delay 50% of maximum, so my VC would be equals to Vs by 2, 50% of Vs, 1 minus e to the power minus t by RC. So it will become e to the power minus t by RC would become 1 minus half, which is equals to half, which is equals to, okay, so it will become if I remove this minus, it will become half, will become 2, it will become t equals to RC log 2. This is the expression that we generally talk about when we talk about delay. Now sir has also discussed, and it's very important thing, this is for such kind of input signal, but generally in ideal cases the input signals are something like this. It has finite rise time and fall time, and for it to account for this for this finite rise time and fall time, actually what happens, the delay, actual delay encountered is more than RC ln2. What is ln2? ln2 is 0.693 RC, ln2 is 0.693, right? So actual delay encountered is more than this. So to encounter for this one, we take it the value as simple RC. Generally it is 90.9 something, but we can take good enough approximation as simple RC. Okay, but we'll be using this expression now. So my TPDF would be equals to ln2 R into C, 0.693. R is how much? R is given as 2 kilo. C is given as 20 femto. Second, do it, you will get the value as 27.72 picosecond. This one is the answer. Any confusion? Is there any comment? Okay, no comment. Any confusion, anyone? Anything you have not understood in these steps? I hope it is clear, because we have been doing this calculation from since class 12 days, right? So that's why I quickly gone through it. But if any confusion is there, please ask me. Please feel free to ask me. Okay. Last two questions. Let us look into it. Find T propagation delay for falling using RC delay approximation for a unit and MOS. Sorry. Cut. Okay, fine. Question number 9. Find TPDF using RC delay approximation for a unit NMOS using of 65 nanometer technology node. The key point is it's a long channel model. Okay, this is the key point. Okay. So we know sir has given this expression, we'll be simply using it, that R switch for long channel is basically minus 2 by VDD and integration VDD to VDD minus VT VDS by IDS at saturation, because from VDD to VDD minus VT my device was in NMOS was in saturation. dVDS plus from VDD to minus VT to VDD by 2, it was in linear region, so VDS by IDS in linear region dVDS, correct? So what happens is, if you solve it, it will become 2 by VDD. I'll be just expanding it a little bit more. VT VDS dVDS by ID saturation is, we know that beta by 2 VDD minus VT whole square plus VD minus VT to VDD by 2, it becomes VDS into dVDS dVDS divided by, it's in linear region, so beta VDD minus VT minus VDS into VDS by 2. So VDS by 2 into VDS. So this VDS will cancel out each other. Okay, and you can see as it is proportional to VDS dVDS term, so it will give me a square term, and it is 1 by VDS term, so it will give me a log term. And sir has already solved it for us and has given us the expression of R switch as, for a long channel, as 3.0868 by beta, that is 3.0868 by mu Cox W by L. So let us put the values and let us check. So it is 80 centimeter square, 3.9, 8.854, 10 to the power minus 14 per centimeter, and W by L, and by Tox is also there. Tox was 1.05 nanometer. Let me write it in centimeter, so 10 to the power minus 7. And W by L, I'll be writing in meter only. It was 1 micrometer and it was 50 nanometer. It is meter, so it will cancel. So let me solve it. Give me a minute. How much I will get? Centimeter will cancel. I'll be getting something as 586.64 ohm. Okay, this is R switch. 586.64 ohm. So now at propagation delay would be, we did it, the propagation delay fall would be ln2 R switch into C load. ln2 is 0.693 to 586.64 into C load is 20 femto second. So basically it will come as something around 8.13 picosecond. I did the calculation, check it once, it will come like this, and the closest answer is 8.12 picosecond. See, it's easy, very easy. Okay, any question? No questions. Okay, let's move forward to our last question of the day. Question number 10. Again, select the correct statement, true, false. So, first of all, what they've asked, propagation delay is a measure of the time taken for a change in the input signal to be reflected in the output signal. So, sir has already told what is propagation delay and contamination delay, but uh, let me quickly go through it. See, say I am having an input like this, okay, and there is a buffer kind of circuit which leads to same input and output characteristics. So if it is my input and if this is my output, then I can define the propagation delay as the time the propagation delay rises, TPDR, as the time taken for the output to get reflected after input has changed. And we take this at which point we take this change, we take at 50% of the 50% of the swing. So if the time at 50% of the swing, if it is my low logic and it is my high logic, then the time from which it has reached the 50% of the input to the time at which it has reached the 50% of the output is taken as the propagation delay for the rise. And similarly for the fall, it will be 50% from the input to the 50% of the output. It is TPD fall. And this rise and fall will be different. It doesn't need to be same. It depends on the capacitances. When you will, because it depends on the PMOS, and the rise one will depend mostly on the PMOS stack and all, and the fall one will depend more on the NMOS stack and how you have designed it. So this rise time and fall time will the propagation delay for rise and fall will not be same, and it may vary, and it generally varies. Okay. Okay. And this is my propagation delay. What is contamination delay? Say I am having one input 1, and I am having a little bit of delayed second input 2, and say the logic was such kind that when my inputs were same, I am getting the outputs as 0, and when my inputs were different, I am getting the output as high. So kind of an XOR gate. Say I am having one XOR gate only. Okay, XOR gate. So you can call it input 1, input 2, or you can call it A or B, and this is the output. Okay. So now what happens? Generally, sometimes there are internal delays between signals due to difference in the path taken by the signals to reach a particular stage of the circuit. This leads to small amount of you can say skewness, or you can say small amount of shift between them. This might happen, and this happens. Okay. For that reason, between these 2 points, instead of getting a 0 output like this, I will be getting something of this order. Okay, this is my output. This is the glitch that we are getting, and this kind of glitches are common in circuits. Okay, so as at this position my output is not what is expected and it is contaminated, it is called as the contaminated delay, the delay between this and this, or this and this. Okay. And to solve this issue, what we do, we introduce some concepts like setup time and hold time. That is, for how much time before the input arrives my clock should be settled, or after how much time my input arrives, after the clock my clock should stay, and I cannot remove the clock, so that all these glitches and all they get removed. So this rise time and for this setup time and hold time concept comes from there. In the subsequent classes, I think sir will be teaching you about this. Okay. So this is that was my propagation delay, and this is my contamination delay. Okay. Now, what is the question? The question is, propagation delay is the measure of the time taken for a change in input signal to be reflected in the output signal. Change in input signal to be reflected in the output signal. So first one is true. Okay. Second one, contamination delay is a measure of the time taken for a change in the input signal to be reflected in the output signal. So it's false. Clearly I said they have given the definition of propagation delay here in the name of contamination delay, so it's wrong, it's false. Third one is contamination delay is measured when the output shows a value that deviates from the expected value. Output shows a value that deviates from the expected value. So yes, it is true. And final one is propagation delay is measured when the output shows a value that deviates from the expected value. No, it's the definition of contamination delay. So it is false. So my answer is true, false, true, false. Answer is true, false, uh, true, false. This one is the answer, correct answer. Okay. Any question in all the 10 questions that I have discussed today? Any confusion, any question? Feel free to ask. Anyone? Hema or Subrat or Vinay? Any confusion? No confusion. Okay, fine. Then that's good. Only 20 minutes left. So I cannot I cannot discuss a new topic. It will take some time. So it's better. If you have any questions or queries, you can ask me, or we can end this session. Okay. So anything. If you have any questions, you can ask me. No questions. Question number 7. Vinay is asking. Okay. Question number 7. What is the confusion that you are having, Vinay? You can type while we're waiting for you, or you can speak also. Explain again. Okay, I'll be happy to explain it to you again. Okay. Let me take it. Fine. See, given see, it is given that R and C are the resistance of an unit NMOS and of an unit NMOS. Okay, so if I take mu n Cox W by L, okay, I have taken everything standard, then the resistance and capacitance I will be getting for an NMOS transistor is taken as R and C. Okay, now we know mu p is half of mu n, or mu n is twice of mu p. Therefore, for same value of W, L and Cox, my R P MOS should be twice of R N MOS, because mobility is half, so current will be half. Therefore, for same VDS, I will be getting twice the amount of half the amount of current, same VDS value. So my RP PMOS will be twice of RNMOS, and RNMOS is given as R. So my RPMOS would be 2R. Clear? Okay. Now, what happens when we scale the NMOS transistor? By scaling, I means if my initial W initial was W, what if I scale my W to a final value which is equals to KW? KW initial, or which is equals to KW. What will happen to my resistance and capacitance? That is what has been asked. Now what I said, that IDS value, the current value, is equals to mu n for NMOS Cox W by L, VGS minus VT minus VDS by 2 into VDS, right? So what is resistance? Resistance is VDS by IDS. Therefore, here resistance will be equals to right here only VDS by, if I take IDS here and this term, this term, if I take this term, if I take in the left hand side, what I will get? I will be getting 1 by mu n C ox W by L. So L will go up, so it will come here, so it will become L by W VGS minus VT minus VDS by 2, right? So you can see R is inversely proportional to W here. Therefore, if W increases, implies my resistance will decrease, and vice versa. If W decreases, implies my resistance would increase. Okay, clear? So if I make my W final into K of W initial, my R final would become K final, R initial by K, because W and R are inversely proportional to each other. Clear? Okay. Any confusion regarding the resistance one? Vinay, any confusion? Is it clear? Okay, it's clear. Fine. Similarly, during capacitances, what I said, capacitance is equals to A epsilon by D, expression for a parallel plate capacitor that we have studied in class 12. Okay, so A is basically my W into T into epsilon by D. So therefore my capacitance is directly proportional to W. If my W increase, implies my capacitance should increase, and if my W decrease, implies capacitance should decrease, right? Okay, therefore if my W final is equals to K of W initial, my C final would be K of C initial, correct? My C would be directly proportional to W, and R would be C would be directly proportional to K, and R would be inversely proportional to K. This is for NMOS, right? So what they have said that the first expression, that if I scale in such a way that my K is equals to 4, my R NMOS would be equal to R by, where R is my initial resistance, R by 4. This one is correct. What about RPMOS? If you remember what I said, that my RPMOS is twice of R. So if I increase the scalability K to 4, if I take K equal to 4, my RPMOS would become, it will become 1/4 of initial, but my 1/4 of initial resistance was 2R. So 1/4 of, for RPMOS, it would be 1/4 of initial R, which was 2R. So it would become R by 2. So this statement is also correct. Is it clear? This PMOS one, I think PMOS one is the one in which you are having confusion. Is it clear, Vinay? Yes, it's clear. Okay, fine. Okay. So, and now, as I already mentioned, that capacitance scales directly with K, irrespective of what is the value of PMOS or NMOS I have taken. So my C PMOS will be equal to C NMOS will be equals to 4 times of C initial, that is C. So this expression is correct, and you can see this is the only one satisfying all the 4 conditions. So correct answer is this one. R NMOS would be equals to R initial by 4, R PMOS would be R initial by 2, C NMOS would be C initial 4 times of C initial, and C PMOS would be 4 times of C initial C, that is 4C. Clear? And when we take Wp as twice of Wn, on that time we get twice the capacitance in the PMOS stack. So on that time it becomes 8C. Okay, so that's why generally in the pull-up network we encounter more delay. That's why if you know about architectures in memory, there are two kinds of architecture: NAND architecture and NOR architecture. NAND architecture is basically stacked NMOS, and NOR architecture is basically stacked PMOS. Stack means in series. We prefer the NAND architecture due to this reason that stacking NMOSes leads to lower delay, because the W is half of PMOS, and thus the capacitance that I encounter is half that of uh, PMOS. The capacitance that I encounter in NMOS is half that of PMOS. Okay, here it is given simple case, so it will be simply equal, that is 4C, both will be 4C. But in if we look into circuit design, you will see that the PMOS stack is offering more capacitance and hence the more delay, because WP is taken as twice of WN. Only this much. I hope it's clear to you. So the answer is R NMOS is R by 4, R PMOS is R by 2, C NMOS is 4C, and C PMOS is also 4C. Okay, hope no one else has any question. If everything is, yes, Shubrat, please. Okay, okay. See, they are not necessary for designing, but these are like, and what will be an ideal, what is MOSFET doing? It is basically working as a switch, right? So what is the ideal characteristic of a switch that we want? See, yes, it should be off. This is what we are expecting. Okay, but we don't get it like this. Okay, because for MOSFET the current doesn't suddenly change in nature. See, if we got some current characteristic like this, we could have got a voltage characteristic like this. But such kind of steep changes doesn't occur in nature. Okay, except in thunderstorm and all, where Dirac delta function kind of expression we get, except that everything is gradual. Okay, so we get something like this instead. So when you go below this V threshold voltage, the current immediately does not switch to zero. Rather, it slowly declines to zero. So what happens basically? Uh, we get something like this, and subthreshold swing is defined as the slope by which my current is reducing. Okay, got it? This is my subthreshold swing, and I think it is subthreshold swing is 1 by id by del VGS, if I remember correctly. Is it the expression? Okay, so it is basically saying that how much quickly my current is reducing when I reduce the VGS. Okay, how much quickly it is going towards zero. And generally a high subthreshold swing is desired, that is as I reduce the VGS, my ID should immediately drop. Okay, this is the definition of subthreshold swing. And what you are talking about, Giddel or Dibble, drain induced burial, Giddel, gate induced drain leakage. Okay, see what happens. To make you understand, I have to go into much more depth of device physics for Giddel. See, simply speaking, there is an oxide here, T-ox, right? What is the thickness of this oxide? Very small, in nanometer. Okay, so in nanometer, not even nanometer, 1 to 2 nanometer, this T-ox is. Have you heard about this term? It is called as quantum tunneling. You have heard about in first year physics, basic physics courses, physics 2 maybe. Okay, what happens if the distance, see, there is a barrier here, abundance of electron is present. Okay, here electrons are present in abundance. Okay, And here electrons are not present, but there are bands available which can have electrons in them. Okay, what happens if this is my Tox, and if I keep on reducing this Tox, if I keep shrinking it, what happens when it reduce it becomes very small, say below 5 nanometer. What happens, due to quantum mechanical tunneling, the probability of finding an electron here becomes non-zero, so you will start having electrons here. And when you apply the gate voltage, if you apply positive gate voltage, what it does, it further narrows down this barrier, right? If you apply in this, if you apply a positive volt here, what will happen, it will go up, sorry, it will go down, right? And this band will go down when you apply a positive voltage, and if you apply a negative voltage, band will go up. So when we are applying a positive voltage in the gate, it further becomes from this it has become this. Okay, it becomes further tilted. So electrons which were initially unable to go, they also start to come here, and then by jumping it goes to there. So there are two kinds of tunneling mechanism. One is direct tunneling, which occurs below 3 nanometer or 2 nanometer, and there is Fowler Norman tunneling, okay, FNT or FN tunneling. It happens below 3 nanometer. It happens below 5 nanometer, and direct tunneling happens below 2 to 3 nanometer. This is direct tunneling. This is Fowler Norman tunneling. This one, this jumping one. So many things happen, but this is one of the reasons why girdle happens. Okay, that's why. And why do we need to shrink this T oxide? Do you know, like when we are shrinking the channel length, why we are also shrinking the y-axis? I think I talked about it in the first class. Okay, so what happens basically, uh, say this is my say this is my how to explain it, say this is my IDVD curve. Okay, so if you look carefully, it is not only dependent upon the lateral direction, it is also it let us take a look into the electric fields present, electric fields and the currents present. So you will know that the electric field components, there are two electric field components basically. One is the lateral electric field that is coming due to this VDS, and there is an vertical electric field which is coming due to mainly due to VGS. Okay, now what happens when we say initial, let me take an arbitrary shape. This is not the shape, I don't remember the actual slope. Say this was my initial, condition, okay, for say 65 nanometer technology. Now I have shrink to 5 nanometer technology. When I have shrinked it, I want my subthreshold slope to increase. Okay, I want my subthreshold slope to improve. It is improving, but if I only scale the lateral direction, the control of the vertical direction increases, and instead of reducing, it might increase. It might show something like this. So we have to scale the vertical direction along with the lateral direction also. That's why we have to reduce this Tox. And now reducing this Tox, this leakage things comes into picture, gate induced drain leakage and all. Now to solve this, what we do, we use we have to increase the capacitance, right? So we use something as called as high K dielectrics, like hafnium dioxide or vanadium dioxide. Generally we use hafnium dioxide. Okay, so what we do, initially we are using silicon oxide, right? Now we use a small pad of silicon dioxide, and above it we deposit hafnium dioxide. So instead, with the Tox of small Tox value also, we are able to reduce the Girdle effect. And this, this quantum tunneling leakage is used in one place. Like it is like, by knowing we use this leakaging in one application. Can you say where? It will not be possible you to say. You know about flash memories that you use in your computer, so SSDs, solid state drives. Like, but you have heard about SSDs, right? So SSDs are mainly made up of a special type of memory cell called flash memories. What it does, flash memories, this is your MOSFET. Okay, no, I am very much excited about it because I work in these fields in memories, so that's why I am telling you with great excitement. Okay, what this does, there are two oxides here. One is called floating oxide, and another is called control oxide. Okay, so when we apply high voltage, what happens? The electrons present here gets tunneled here, starts tunneling, and electrons accumulated here. So when charge, if you remember from your physics classes, semiconductor device physics, in your second or third year, you remember. Okay, okay, so let me give you a brief idea. What happens? This threshold voltage of a MOSFET also depends on the charge present in this oxide region, TOX. Okay, so basically by this we are inducing electrons here, so we can simply shift the VT. We can change the VT. So if initially my current characteristics was like this, now I can shift the VT and make it like this. And here if you given voltage, initially if the current was low, for this characteristic, now the current has become high, so it starts behaving as a memory device. You can store the value here permanently. So this is how the flash memories work. They exploit these Gödel effects and all, this quantum mechanical tunneling, direct tunneling, and FN tunneling. Okay, so this is how we do it. So this is the basic. Here lots of research is going on, and this is really a very interesting field to work upon. And also, due to this tunneling, you can understand as electrons are going through here, so the quality is generally of it is quality is degraded over time. That's why the flash memories nowadays in servers, if you see, like Google server or Facebook server or any other server, they have to keep on replacing them every 2 years or 3 years, because due to this tunneling, the quality of the oxide degrades with time. Okay, so I went far off from the field, but as you are interested, that's why I brought this point in front of you. I hope it's clear. Okay. Yes, Uttara, you want to say something? Okay. Okay. So if anyone, no one else has any confusion, so we can call it a day. I hope everyone understood what I tried to teach, what I tried to convey. And if there is any confusion, please get back to me via mail or something. Okay. Okay. Thank you. Have a nice day. Bye.